Hello, this is must be episode 3 of chapter 6 of S. Hogman's A Brief History of Stuff and Shit. So, as you should recall, if you watched chapter 1, this is Black Holes. I mean chapter 6, this is chapter 1 for me, this is chapter 6 of S. Hogman. Anyway, we'll continue with a guy who has a hard name to say, as you will remember from the last episode. Chandrasekhar realised, however, that there is a limit to the repulsion and the exclusion principle can provide. Good stuff. See, the name proves. Chandrasekhar realised, however, that there is a limit to the repulsion that the exclusion principle can provide. The theory of relativity limits the maximum difference in the velocities of the matter particles in the star to the speed of light. This means that when a star gets sufficiently dense, the repulsion caused by the exclusion principle would be less than the attraction of gravity. Chandrasekhar calculated that a cold star of more than about 1.5 times the mass of the Sun would not be able to support itself against its own gravity. Brackets. This mass is now known as the Chandrasekhar limit. A similar discovery was made about the same time by the Russian scientist Lev Davidovich Landau from the Star Wars series. This has serious implications for the ultimate fate of massive stars. If a star's mass is less than the Chandrasekhar limit, it can eventually stop contracting and settle down to a possible final state as a white dwarf, with a radius of a few thousand miles and a density of 100 tons per cubic inch. A white dwarf is supported by the exclusion principle repulsion between the electrons in its matter. We observe a large number of these white dwarf stars. One of the first to be discovered is a star that is orbiting around Sirius, the brightest star in the night sky. Landau pointed out that there was another possible final state for a star, also with a limiting mass of about 1 or 2 times the mass of the Sun, but much smaller even than a white dwarf. These stars would be supported by the exclusion principle repulsion between neutrons and protons, rather than between electrons. They were therefore called neutron stars. They would have a radius of only 10 miles or so, and a density of hundreds of millions of tons per cubic inch. At the time they were first predicted, there was no way that neutron stars could be observed. They were not actually detected until much later. Stars with masses above the Chandrasekhar limit, on the other hand, have a big problem when they come to the end of their fuel. In some cases, they may explode and manage to throw off enough matter to reduce their mass below the limit, and so avoid catastrophic gravitational collapse. But it is difficult to believe that this always happens, no matter how big the star. How would it manage to know that it had to lose weight? And even if every star managed to lose enough mass to avoid collapse, what would happen if you added more mass to a white dwarf or a neutron star to take it over the limit? Would it collapse to infinite density? Eddington was shocked by that implication, and he refused to believe Chandrasekhar's result. Eddington thought it was simply not possible that a star could collapse to a point. This was the view of most scientists. Einstein himself wrote a paper in which he claimed the stars would not shrink to zero size. The hostility of other scientists, particularly Eddington, his former teacher and the leading authority on the structure of stars, persuaded Chandrasekhar to abandon this line of work and turn instead to other problems in astronomy, such as the motion of star clusters. However, when he was awarded the Nobel Prize in 1983, it was, at least in part, for his early work on the limiting mass of cold stars. Chandrasekhar had shown that the exclusion principle could not halt the collapse of a star, more massive than the Chandrasekhar limit. But the problem of understanding what would happen to such a star, according to general relativity, was first solved by a young American, Robert Oppenheimer, in 1939. His result, however, suggested there would be no observational consequences which could be detected by the telescopes of the day. Then the Second World War intervened, and Oppenheimer himself became closely involved in the atom bomb project. After the war, the problem of gravitational collapse was largely forgotten, as most scientists became caught up in what happens on the scale of the atom and its nucleus. In the 1960s, however, interest in the large-scale problems of astronomy and cosmology was received by a great increase in the number and range of astronomical observations brought about by the application of modern technology. Oppenheimer's work was then rediscovered and extended by a number of people. Light ray emitted at the time the event horizon falls. Signal, alright? No, signal. Singularity. I said signal. No. Signal, alright? Light ray emitted after event horizon falls. Light cones. Why going this way? This is time. Which line is time? Distance from the centre of the star this way.